Before we start, let me ask you a question. So how did you like yesterday's session? Okay, so how about doing the same on Friday? Okay, that's what we'll do then. Okay, today we're going to have a clean contest in the afternoon. Tomorrow, a session like this. Started with the fourth day. The plan for today is as follows. Today we're going to start with problem set discussion. We'll discuss the blankets from Tuesday and some problems from yesterday. This should not take too much time. After that, as I said yesterday, we're going to focus on the test candies from Baltic Olympiad in 2010. I think it's worth discussing because it has like lots of very useful techniques in it, and so there are some really nice ideas inside the solution. And after that, the second part would be some kind of a short talk about different tips and tricks for programming content. So first, I'd like to give you some tips on things like strategy and what you can do during the contest, except for solving tasks to get better results. But also, I'd like to give, in the very end, I'd like to give you some technical tips, like how to speed up your program without really changing the algorithm, how to reduce the memory usage, and so on. So maybe you'll know some of them, but I think others are, well, at least some of those tips are not really well known. Right, so let's start with the task blankets. The task was as follows. We were given some, 8 by 8 rectangles that were all aligned in the same way. Like this. So on. And the task here was to compute, well, the average intersection of two rectangles, the average area of the intersection of the rectangles. So the way we did it, we could compute the total, the sum of all intersections of all pairs of rectangles, and then divide it by n times n minus 1 by 2. The sum of area of intersections. Now, since this number can be very big, you could either use long double to store it. This actually turned out to be enough. If you wanted to be sure that it's not going to overflow, you could have kept it as a fraction, like a plus b over n times n minus 1 over 2. So you basically kept like two long values, this one and this one, and kept adding it to this format. So both versions worked. This maybe was a bit safer. Right. So now the problem is how to compute the sum of all areas of intersection. To do that, we'll this is not a surprise, I guess. We'll use the sweep line technique. And we consider the possible ways in which rectangles can intersect. So one is like this, and the other one is like this. So, oh, sorry, these are not the same. So what I'm saying is that the rectangle to the right is either higher or lower. Well, okay, it can be at the same height, but it's like one of those cases. So let's focus on this case, right? So we'd like to compute this area. Then in a very similar way, we can compute those areas. So what happens here? This point has some coordinates x, y. And this point has some coordinates a, b. And the area of the intersection is, well, it's x minus a times y minus b, which, not surprisingly, is x times y minus x times b minus a times b plus a times b. So we have to compute. So for every two rectangles that intersect, we'd like to compute this. On a step, we'll compute this thing, and actually we'll compute every term here, sort of separate. So what is it? Let's take a look at it. So what happens is that if we have a point xy, we take a look at the rectangle looking like this, and for all points inside this rectangle, in which there are corners looking like this, right? And for each such corner, we'd like to add this, right? So let's do that. So how to add this? Well, we have to add xy, x times y, which we know we are in this point right now. So we have to add this as many times as the number of points here. So it just suffices to count how many are there. And then this is minus x times b. So we know x. So what we need to do is just sum the value of b of all these points, right? So like we can do one algorithm to do that, one algorithm to do this thing, right? Just sum the number, and then well, conceptually have a totally different algorithm that would do this. We'll just with every point we'll associate its second coordinate and just add these values. And to do this, well, we have to subtract the product of coordinates over all points. So here, another sweet line algorithm that with every point associates the product of its coordinates. And we sum this. And then, okay, this makes no sense. AY. And then here again, we know the value of y. We need to get the sum of the values of a over all these points, right? So each of those four algorithms is pretty simple, right? So what we need to do is that we basically it's width by height. So what we do is we use a sweep line algorithm, and every step we remember in our data structure. Say we're in this coordinate right now, and we remember all points that are at distance at most w to the left. So this is what we have in our data structure, and then we have one data structure that allows us. We have one data structure that allows us to count points in some interval, size h. We'd like to count how many are there points with coordinates from y minus h onto y, and then we have another data structure that allows us to sum the values of b over those and so on. So is it clear how it works? Okay, and then if we add up those, we will effectively sum those terms, and this will give us the desired total intersection area. So this is conceptually like running 4 different 3-line algorithms for computing each of these terms, and then we add it up together. Of course, the data structure that we use will be some kind of segment tree. We have to use something pretty smart here to get it running, but it's well, there are many variants. Like one, we simply have to, since we have all these points, get all these lower left corners here. One data structure will be has to be able to just count the number of points in an interval. Another one has to be able to sum. So with every guy with some value associated, that we have. Sorry, we have to be able to sum the values from some interval. And this is how you get it done. So I saw someone solve it. So was that the way you used?
No. I use segment tree with lazy propagation.
Lazy propagation. Can you describe it?
Yes. Well, it contains 2 operations. I mean, do you mean the whole problem or the segment tree with lazy propagation?
Maybe you should just give us your idea. Like, can you come and draw it briefly?
Well, I also started this.
Right.
Well, my idea is, suppose that for each column of the grid, we want to calculate how much does this column contribute to this sum, the upper part. Well, we have some rectangles that intersect here, and we process them in order, in some order. Doesn't matter which for now. Then for each rectangle, we put +1 here, the intersector of the column. Then for the second column, second rectangle, sorry, we first carry the sum of these numbers, which is 1. So for now, this column contributes by 1. And then I add 1 for each of the cells that intersect. So we get a 2 here, 1 here, 1, and 1. Then for the next, we carry get some this here, like 3, and add 1.
So basically, at every y coordinate, you remember what is the number of rectangles currently here, right?
Yes, at each of these coordinates.
Yeah.
And then for each column, I have how much it contributes for this value. Well, this value for each column, let's call it Ci, only changes at a few points, the start and the end. So I run a line flip, and at each of these special places here, I update this value of each count, and I multiply the old value by how much we run. That's a line flip. So, and then to solve this structure, we use segment tree with lazy propagation.
Right. Sounds good. Okay, thanks. Any questions? Okay, so let's then move on to yesterday's tasks. I think we should skip Stonegate. There's not much we can say about that. Let's go. Okay, most of you solved it, but I'd like still to discuss it with maybe 2 minutes. Logarithm. So we're given some huge number, b, and we have to compute log a b, where a is between 2 and 40, and b is about 10. Well, it has a close 10 to the 5th digits. And there are 2 ways you can do that. One of them, it's kind of a, well, let's say it's a bit messy, but I mean, it's maybe not entirely clear why it works, but what it does is that, well, you should realize that we have kind of too much information here. So we have all digits of B, but actually you can recognize the result by just looking at maybe, I don't know, 8 most significant digits of B plus the number of digits in B, right? Because this actually tells you what the logarithm is. I mean this is sufficient to detect it, right? Because every time you multiply B, even by 2, the first digits change a lot, and actually after every few multiplications, the length of B increases. For example, if A was, say, 13, then we could just simply use the length of B, right? And it will tell us what the result is, right? Because the consecutive powers of 13 get longer and longer. So every next power has more digits than the previous one. So actually we could have used just the number of digits of B to get the logarithm. So if we want to compute log 13 of B, and B is like, well, say B has, I don't know, 20 digits, so it's 10 to 19. So we can actually, if we replace B by just any 19-digit number, it's 10 to the 19. And this is equal to 90 times log base 13 of 10, and we get some fractional number. And actually, one can observe that this fractional number would be actually very close to the right result. Now, this works if A is at least 10. Sorry, but if A is less than 10, what we might do if B is, say, I don't know, huge number. Say it has like D digits, so we can say that B is roughly equal to 1, 2, 3, 9, 7, 4, 5 times 10 to the D minus whatever. 7, whatever, something. Yeah, so we can just get rid of all these digits, and we change B by only slightly, and then if we have a number like this, we can compute logarithm easily. It's a small number. I mean, we can use the formula, which says that log from base A from 1, 2, 3, 9, whatever times 10 to D minus 7. This is equal to D minus 7 log A of 10 plus log A of this number. And you can show that by doing that, you'll get a number which is very close to some integer, and this integer is indeed the logarithm. So we don't lose much by just changing all of those digits to zeros. The other approach here is a bit smarter, and it's also you don't have any doubts that it works. So basically, what we have to do in this task is to solve an equation: a to the power x equals b, right? So instead of solving this one, let's solve the same equation mod, say, some prime number, 10 to the 9 plus 7. So we can easily compute b mod this, right? We can just take this number and process digits one by one. We start at 1, then we multiply by 10, add 2, multiply by 10, add 3, and perform all these operations mod this. So we get b modulo prime number. So now we have to find some x such that a to the power x equals this b modulo b. From the input data, it's easy to calculate that x is small. It's between 0 and something like 400,000. So we can actually take A and compute all those powers, just one by one, starting from 0 power and going all the way up. And now, for at least one value of x, the x to the power of x will be equal to b mod p. I mean, there has to be a solution to this equation. But not only that, actually, from number theory, we know that if p is so big, then the first, I don't know, something like p minus 2 powers of a modulo b are all distinct. So actually, we're getting a single value of x which satisfies this equation, and we get the solution to the problem. Right, let's go to byte rate now. In the byte rate path, we were working with a graph which was looking like, I don't know, a bicycle wheel. So there were some distances here. And so on. And the goal was to compute the pair of most distant vertices. So let me do this one very briefly. The first step was to realize that how to measure distance between 2 points. We have 2 vertices here. There are 3 ways the shortest path can look like. So first one, it does not use the middle vertex. That's case 1. If it does not use the middle vertex, then it either goes like this or goes like this. So in both cases, this is just a distance along the line, and we can easily pre-process that so that we can compute those distances in constant time. Now, the second case is that the shortest path goes through the middle vertex, but then it goes to the middle vertex with the shortest path possible, and then from this middle vertex, it goes here with the shortest path possible. So we can compute shortest path from this guy, all other vertices, and we can compute the incoming shortest paths and outcoming shortest paths. Well, we have them computed, so we can get those again in constant time. So now we know how to compute the distance between any pair in constant time. Once we get that, we have to use binary search. So this is actually a tricky part because it's one of the moments when, okay, it's difficult to figure out what to do, but a very strange approach, like, okay, let's try listing all the techniques I know in my head, might actually work. Because I mean, I was talking to people and I said that, you know, it's binary search, and they were like, okay, I know how to do it. So sometimes it's useful. If you don't know what to do, just try, I don't know, have a list of the algorithms you know and try matching all of that to your problem. Maybe this would help. So the binary search works like, given an x, check, is there a pair at distance greater than, well, at least x. How does this work? Well, it works as follows. We're going to do that for every vertex on the side. And so we have some vertex here. We know that, for example, we can go all the way, using this arc, all the way through here with this. This is distance at most x. And also we can go all the way up to here around with distance at most x. And to check if there is a vertex at distance more than x, well, this vertex will have to be here, somewhere in this interval. So basically, if we count that, well, with distance x we can get here, we can get here, and to these vertices we'll have to go through the middle. So we go to the middle, we spend some distance d, and now we check, is there a vertex here on this arc whose distance is at least x minus d. If there is one further from here than that, then we found a vertex at distance at least x. And then we're we take this point and we keep rotating it around this bike ring. So those two arcs we're going to move, and we'll have to just answer queries like what is the vertex which is furthest from the beginning in some part of the outer arc of the bike ring. Of course, there's also a special case when the pair of most distant, well, one of the most distant vertices is the middle one, but this is a very easy one to consider. Right, so this is how you did that, and it's like n log n for the distances, and then another n times, well, it's n log n plus n times log maximum distances, because you have to define a circle over all distances, and this is the running time we get. Actually, maybe we need another log here to compute the answer queries like what is the maximum distance. Yes?
We follow the experiments of the problem.
Okay.
You do a dark strip on the center of the graph and find the furthest. Then you do a dark strip again for a node and find the furthest.
But that doesn't work.
You got the center.
Yeah,
but we have a comprehensive.
Okay, you should have counter example then.
Because right, just a piercing.
Okay.
It has 3 vertices.
3?
Yeah, in the
Like this?
No, 3 in the circle. Yeah. And all the 2 edges on the circle have weight 1, the other one has weight 4. Yeah, and all the edges to the middle have weight 1. So if you do diagram from the center, you can get to any vertex.
Okay, from center we can get anywhere, right?
Yeah, so if you choose
This one?
this one, the diameter would be 1.
Yeah, you can go from here to everywhere with 1.
Yeah, but the diameter is actually
It's 2.
2. Yeah.
Yeah. So it does not fit. Okay. Yeah, good for you. You managed to challenge the test data. Challenge succeeded, right? Okay, so I think that we'll have to stick to this solution. Right, so let's move on to lowers. Because glowworms, this task was all about geometry. So we had some worms that were moving with some speeds in various directions. And the task, well, it all started at moment 0. They started moving, and the task was to compute some moment in time in which all these points can be enclosed in a square which is as small as possible. So what you have to do to get this task solved is to observe basically one thing, is that if we draw the timeline, time goes here, and at every point there is some dimension d of the rectangle that's enclosed, of the smallest rectangle enclosing all the points, then actually the function looks like this. So it's a concave function. It may start decreasing, but after some time it's only gonna decrease. And intuitively it means that, well, there are two points that might be going towards each other, but once they pass through each other, then they'll be just going further and further. More formally, we can consider this problem well, in both dimensions separately. So so yeah, if we consider just the if we want to enclose all the points in the narrowest possible stripe, looking like this, or well, this is all happening in one dimension. So we have basically some some points moving various ways. And here I think it's easier to see that. And what happens is exactly that. I mean, the points might be getting closer to each other, but at some point there will be a point here and a point here, and one will be going this way and the other will be going this way. And from this time, this square will just grow. Okay, this can be proved formally. Maybe it's not very important now. But once we get to this observation, it becomes pretty easy at least to come up to the solution. So this is a convex function. We have to find its minimum. We just use ternary search, right? The algorithm we talked about yesterday. Just you can evaluate the value of this function at every time step easily. So basically, if we want to check what is the value here, we have to, okay, this is time x. We can, for every point, compute where it's going to be after time x. And after that, we just have a set of points we need to enclose with the smallest rectangle possible. So this is trivial. We just find the one first to the left, first to the right, topmost and bottommost, and we know that we have to bound those. Right. So I think the tricky part here was to get it right with floating point numbers, and I think it's a good lesson because I saw that many of you had some trouble with that. And my advice on that, well, I have two pieces of advice for you. One of them is that when you're solving the task with floating point numbers and it doesn't work, then immediately switch from using double to long double, or maybe even better, don't even try to start with using the double variables. Just start with long double. But secondly, and probably more importantly, don't. Okay, here you have to run this ternary search for some number of iterations, and sometimes you set some epsilon and so on. And so my advice here is don't try like using the same number in every program you write. Just in every case, try to calculate what is the precision that you need, what is the number of iterations you need, and how many do you have to do in order to get it correct. So it's never a good idea to have, I don't know, a line like epsilon is equal to 10 to minus 8 and use this forever. No, it really depends on the problem you're solving. So how to do it here? Well, the speed vector of every worm can be at most, I don't know, 2 to 10 to the 6th. So this is how much a single worm can move in a second. And the precision we have is the required precision, right? So this means that if we want to capture the movement by that low, and every second a worm can move that much, it means that we have to check every time step, like every roughly 2 to minus 9, right? So we have to divide this by this. 1 second of that. Right? Because within that much time, the glowworm may move by this distance, and this is the precision we have. So we really have to check points in time which are that many apart. So what happens now? We're using ternary search. We start with, well, we have some variables like left and right side of our interval with what we're considering. So we start with L equal to 0 and R equal to whatever. I don't know what was the right answer here. Say it's 10 to the 10th. So initially the interval has length 10 to the 10th, and we want to get it down to 10 to minus 9. Well, actually, to be safe, I would assume something like minus 10. And so the question is, how many iterations do we need? Well, at every iteration, the length of the interval changes by 2/3. So what we need to do is we need to calculate, well, basically 10 to the 10 we have to multiply it by 2/3 to power x to get it to be something like 10 to minus 10. And this is the kind of calculation you really have to perform before setting the iteration limit to know how many you have to do to get it right. And I think that this is like a few hundred, so it's quite a lot. Right, so let us move on to planar graph. Planar graph, the most difficult task from yesterday. Actually, we got one correct solution. Unfortunately, it used too much space. In the second part of the morning session, I'm going to tell you something about reducing space, so maybe some of the tricks would be helpful here. So the planar graph task, the input was a planar graph. And it had at most 2 faces on sides. It was connected. Even two connected. Two connectivity is, I'll tell you what it is for. It's not really important, but it's just to make life easier. And now the question was, divide the edges into cycles of even length. Right. So the approach, okay, there are, I think, 2 approaches for tasks like that, like, well, we have to divide it or say that it's impossible. Or say, so when we have a task which requires checking some complex condition, and you're trying to think about it and you really have no clue about what the condition might be, try thinking of some obvious conditions, like list as many necessary conditions as you can, and sometimes it happens that the simple necessary conditions are actually sufficient for the problem to work. So what are the obvious conditions here? Well, the first one is that the graph has to have an even number of edges. Like we're dividing it into even cycles of even length, so the number of edges has to be even. The second one is, well, we're dividing this graph into cycles, so it basically has to have Eulerian cycle. Well, it's connected, so this has to hold, and this is actually equivalent. Maybe it's an easier way to put it, that the degrees are all even, because well, every cycle has 2 edges incident to a vertex, so all the degrees have to be even. And it turns out that these 2 conditions are sufficient for the solution to exist. Of course, right now it's not, okay, it does exist, but we have to restore it, and it's not obvious how to do that. But this can also be done. After we did that, the second step is to use one of the planar graph techniques, and here the right technique was duality. So with duality, given our graph, we build a dual. So here, this is a nice example like someone was drawing. This is a graph with 2 odd faces, but it still has a solution. I mean, you can take those 3 squares. This is the dual graph. Well, okay, this is. This one. Now, when we're going to the dual graph, we have to transform these conditions into equivalent conditions for the dual graph. So, okay, let's skip this one. Well, okay, even number of edges in the primal graph is the same as even number of edges in the dual graph, because the number of edges are just equal, right? Now, the even degrees. So when we're going to dual, the vertices become faces. So even degrees, they mean that in the dual graph, every face will have an even number of sides. All faces have even number of sides. So we have a planar graph in which the faces have even sides, and now what we can get about the graph is that if the planar, so this is some not very difficult fact. A planar graph in which all faces have even number of sides is actually a bipartite graph. You can color it with two colors. So this means it's bipartite. So now our planar graph drawn as a bipartite one might look like this. This is a very non-planar drawing, but assume what I draw is corresponds to a planar graph. So we have a bipartite graph which has even number of edges, and at most two faces have odd sides in the primal. So again, at most two faces have odd size in the primal. The faces converge to vertices in this graph. So here, at most, two vertices have odd degree. Right? So now we've converted this condition to the dual. We have this one in the dual. We have even number of edges. And we've converted this one to the dual, and this converted to the dual is bipartite. Okay, so where can those two odd vertices be? Well, okay, say they're on opposite sides. What does that mean? That means that from this side, we have some even number of edges going from here, even number of edges going from here, even number of edges going from here, and odd number of edges going from here. So now observe that if we count edges going from the left side, that we can count all the edges, right? I mean every edge starts somewhere in the left. So if there is exactly one odd vertex here, and we count all edges leaving the left side, we get an odd number. So this can happen. We have an even number of edges. So the two vertices it's not possible for the two odd vertices to be on two sides. So they both have to be on the same side. Okay, and this is the moment when we're almost there. So we have a dual graph in which one side consists of vertices of even degree. These vertices are faces in the primal. These faces all have even number of sides. And moreover, these faces cover all edges. So this means that what just happened is that we have shown that we can color our graph, color the faces of our graph with two colors. So we draw the example before. Once we check if those conditions are satisfied, we can color the vertices of the dual graph. So we color the faces of the triangle graph with two colors, like a chessboard, in the ways that the adjacent faces have distinct colors. So if two faces share an edge, they get distinct colors. And now, either the blue faces or the green faces all have even length. So we can go around every blue face and we'll get even cycles, or we can go around all green faces and we will get only faces of even length. One of these two has to hold, and we can just output the cycles that we want to output would be just basically faces of one or the other color. Any questions about this one? All right, very good then. So that was the problem set from yesterday. Do you have maybe some other questions or comments about yesterday's session? The plan I mentioned in the morning is to do something similar on Friday. Maybe the only difference is that we might have a bit more tasks than we had yesterday. Okay, if not, then let's go to the problem candies that I introduced yesterday, and this will be the second part of this session. As I said, task candies, although a seemingly simple one, has some very nice techniques for solving it, and that's why I'd like to discuss it with you. So instead of a real lecture, we'll have sort of a case study and hope to learn something different. Yes.
So yesterday you told me blankets that
Yes, I think we did. Excuse me?
You said you solved the blanket test.
The blankets?
Yes.
I think we did that, right?
Okay. Yeah. All right.
Okay, now you're confused. I think this is what we started with. Okay, so it's candies. So the task candies again is we have boxes with candies with A1, A2 up to AN. There are most hundreds of those. We have boxes with candies, and each of this I box has AI candies in it. And then every AI is close 7,000. Now a customer comes and asks for M candies, and when he does that, the shopkeeper wants to bring boxes with a total of M candies and give them to the customer. So if we have boxes with 1, 2, and say 3 candies, it's possible for the shopkeeper to serve orders. Well, if someone wants 1 candy, he can give it this box. In case of, for this example, 1, 3, and 4. If someone wants to get 2 candies, it's not possible because there is just 1 box with 1 candy, so it's not possible to give someone exactly 2 candies. With 3 candies, it is possible. With 4 candies, it is possible. With 5 candies, it is possible to get 5 the box with 1 and 4. And then with 6, it's again not possible. With 7, it's 3 plus 4. And with 8, it's 1 plus 3 plus 4. So basically, if we have this set of candies, we have the following set of options. We can give, well, 0, 1, 3, 4, 5, 7, 8. And for example, if our set of candies was say 2, 2, and 2, the set of options would be 0, 2, 4, and 6. So is it clear what are the options here? Okay, so I mean this is crucial to understand this concept because I'll be using this a lot. So now the task here is change the number of candies in exactly one box so that the number of options increases by as much as possible. Now, there can be many good solutions. So, to find the right one, if among changes from, say, P to Q, so we take a box with P candies and change it to Q candies, output first, minimize P. Second, once you minimize P, minimize Q. Okay, that's what we have to do. And this is actually quite important. We'll see that in a second. It's a bit more complicated because of that. So the first observation is that this task is actually two different tasks. Where we have to solve the first one and then we have to solve like a completely different second one. Why is that? Well, we can say that instead of changing the number of boxes in one candy, we first take one box and destroy it, and then we add one new box. It's like the same as changing. So now my question is, let's say we have a set of boxes, and we can add one new box. How many new options can we add?
The number of options you add 4 plus 1. If you had x options with the set of boxes, then you add only 1, you add 2x plus 1.
Well, I think if you had an option of 0, then it's just twice as much.
Oh, I didn't know that.
Okay, well, I mean, yeah, you're right. So if our set of options is like whatever, 0, 1, 5, 10, 13, I have no idea if this might happen if there is a data for which this happens. We can add a box with, I don't know, 100, right? And we get options looking like 0, 1, 5, 10, 13, and then 100, 101, 105, 113. So the first observation is that we can double the number of options by adding one box. Adding one box doubles, or may double, the number of options. So, because of that, we will do this in 2 stages. Stage 1, remove a box that so that the number of options decreases as little as possible. And now step 2, add the smallest possible box that doubles the number of options. So in the second step, we can always double the number of options. We can't do better than that no matter what we do. So we can do greedily. We have to remove as little options as possible here, and then we double them and get the result. Right? So we can solve these two parts independently. Okay, so that's why I said these are two tasks, and then also this is why this has to be minimized, right? Because if we don't have to minimize Q, this Q we can just take some enormous number here, and the number of option doubles, and the second stage will be easy. So now, actually, the challenge in the second step is not to find a box that doubles the number of options, but to find the smallest such box. Okay, I think I have to erase this now. Okay, so now, stage one. So let's start with recalling how to compute the number of options. So what we need is an array. Okay, I'll write some CPP code here. Yes?
How do I know there is not a better solution that don't double the second stage?
Well, every solution is like remove some box and then add a new one, right? So okay, I take this optimal solution and I remove the box that it does remove, right? So I follow this optimal solution here, and then I cannot. Okay, in the second step, it's not possible to do better than double, right? Okay, so I take my solution that changes this super solution that changes P into Q. So I have to remove P in this solution, and here I know that it's going to double the number of options, right? So, okay, so I have like X options at the beginning, I remove P, P and I remove it. I get to Y's options, then I add Q, and then I get Z solutions. And Z is, and let's say this is an optimal solution. So I know that, I know that Z is not more than 2y. It's not possible to do better by adding a box than double, right? But also it's optimal, so it's actually equal to 2y. So the optimal solution may do that. Because, so again, I remove P, so I take this optimal solution and I remove P, right? And then, okay, I took half of the optimal solution to that line. And now I can add some huge box to the set of boxes I have, and I'm going to double what I got. So I can follow the first step of the optimal solution and get to y, and that, as we've shown before, if we have y here, I can go from y to 2y in one step, because I can add a very big box. So okay, again, so you don't have to minimize the sizes first. So you first want to have the maximum number of solutions possible, and among those, that means the maximum number of options possible, and among those, you minimize the size of this box. But this is like, you first want to maximize Z. This is your main goal.
My doubt is, I don't know if that's possible, but if I have 3 options at the beginning,
yep,
and 4 options. I have 4 options, and I take one box, and instead of 4, I now have 3 options.
yes.
And I can't double, but I can change.
No, you
I can add
so
one.
my point is that you always can double.
Yeah, suppose I can double.
No, but you always can. that's
Always.
yes. So, okay. So let me recall. So let me recall this one. So if your set of options is like whatever, -1, 0, 1, 5, and 8. If you had like a huge box, like with 1 million candies, right? You can get either of those. By huge, I mean bigger than the sum of all those. You can get all these options plus, no, million plus 0, and then million plus 1, and then million plus 5, and then 1 million plus 8. So you can always double.
I misunderstand. I thought you took, I don't know, you took any box from one box and then you add any box to other.
No, you take one box and you destroy it, and then instead of this destroyed one, you add a new box. So then you really kind of divide it into 2 stages. Okay, so is it clear? Okay, yeah, so you destroy one box and replace it with another box. And then that's why in the second step, you can always double the number of options and you can solve the 2 stages in a method. Okay. So, some C++ code for computing the number of options is 100 plus 7,000 plus 1. Okay, I'm writing this from my hand. That's how I don't get it wrong. So, okay, so initially this is all 0. All set to 0. And then I always have the option of giving 0 candies. And now I go through all boxes. Now, I usually don't write code, but in this, I think in this case, it actually makes a lot of sense. You'll see it later. So I go through all boxes, and for each box, I kind of add the information about this box to this array. So I have to go now from j equal to 100 times 7,000. Then j has to be at least a of I, j minus minus, and then dp of j. Well, you can write it like this. So if dp of j minus a I is 1, then dp of j will also become 1. Now, here, this is 100. So, right, so, sorry. So what's happening here with a standard dynamic programming approach, we have this array which basically says dp of I is like, is I an option? So initially, this is all 0, we have no options. Well, okay, we always have the option of giving 0, and then for every box of candies we have, we add the new options that it's giving to us. So this loop is going from top to bottom because we can use each box only once. And then if we have an option of getting something minus I of I candies, then we also have an option of getting this number plus A of I candies. Now I wrote this code because I want you to think about what's happening here is of a data structure. So we have a data structure which has an operation add one box. It's a data structure for counting options. And it has an operation add a box. And this operation runs in, what's the running time? Excuse me? Yes, it's n times n. the operation of adding a box is n times m. It's basically these two lines, right? Okay, so initially we can compute the total number of options for all boxes. The problem is that we want to kind of know this number of options for all n minus one subset of boxes. So although we can compute this data structure and that will represent all boxes, we actually wanted to have it for all sets of boxes that do not contain some specific box. And while we can add to the data structure, we don't really know how to remove, right? Because what we want to do is, well, we'd like to compute this data structure and then do something like, okay, remove first box, and now check the number of options, and then add it back, and then remove the second box, check the number of options, and so on. And this way we'll know which removal decreases the number of options as little as possible. The problem is we cannot do that with this data structure. But what we can do is we can do as follows. Okay, here are the n boxes we have. Let's divide it into blocks of root n boxes. And we'll do it as follows. So first, we'll compute the data structure for all these boxes. Okay, we have all boxes added, and then we'd like to get it for all subsets that do not contain one box from here. So now we compute this data structure, we store it, like we copy it and have it somewhere. It's like copying this array. And then we'd like to know what is the set of options if we take all boxes but this one. So we take this data structure we've copied and add these boxes except for the last one. And we got the number of options with all boxes except for this one. And then we undo. Now we'd like to compute the number of options with all boxes except for this one. So we add these boxes and the last one, and we got the number of options here. And then we go and we do this for every box. We add all boxes except for this one and then all others. And we get, again, the data structure representing all boxes without one. So how much time is it going to take us? Well, this is all for the case of, so after some time we get information for every missing box from the left block. And of course, once we did that, we throw away what we got, and we now build a new data structure that represents these boxes and these boxes, and we again copy it somewhere, and then we would like to focus on this block. So we add all boxes for each box here, we add all boxes except for this one, and then for this one, and so on. So now, how much time is how many add operations do we have to proceed? This is the way to think about it. So there are root n blocks, all of them. In order to compute the data structure for everything except for the block, we need basically add operations. We have to do, well, it's n minus root n, but it's roughly like n. And then for every box here, so again there are root n boxes. We have to, so if we fix the box here, we're adding all boxes except for this particular one. This is again root n time. So altogether we get n root n add operations to produce the data structures for all sets of boxes, excluding some specific one. Okay, let me give you some time to digest this construction.
the analysis of the data.
The analysis, sure. But so you know how the algorithm works, right?
Yes.
Okay, so we go block by block, right? So there are root n blocks, each of size root n. So now this is what happens for a single block. So if we, for example, fix this block, then the first step is to compute the data structure that contains all boxes except the ones in here. So we have to add, well, we have to add n minus root n boxes, but it's like the same as this one. I mean, minus root n does not change much. So I'm just writing n here. This is for computing this data structure for all guys except for those. And then I have to do something for every box in here. So this is this root n. For every box in there, I have to perform, well, if I fix one box, I perform roughly root n add operations. And it's this root n. So I get n root n add operations. So and each operation, again, I should also add that each operation takes this much time. So I get a total of n squared root n times m running time for solving the problem. And this is good because if I simply wanted to, I don't know, like if I was simply going box by box and I would be saying, okay, take this box and build the data structure for everything except for this one, I would get something like n cubed m. So this is already getting better. Questions? You're just waiting. Okay, but actually we can go further with this approach. So it's sometimes the case that if you have an algorithm with a root n, well, this algorithm can be drawn as a tree. In the first level, we branch into root n blocks, and then for every block, we go through all root n elements of it. And actually, our algorithm can be represented by a tree, so with like 3 levels. And here we're branching by root n, and here we're also branching by root n. And it turns out that we can go from here to a binary tree. Much unexpected as it may sound. Okay, so what happens? Well, our algorithm will follow a schema like this. Let me show you a binary tree, and then I'll tell you what is it doing. So we have boxes here. Say boxes 1, 2, 3, 4, 5, 6, 7, 8. And we have some nodes of this tree. Say this node is, let's call node by the leaves below it. So let's say this node is V1, 2. This node will be V1 to 8. So it's like the interval of leaves below it. That's how I'm calling those. And this one is V5 to 8. And now what I'm going to do is I'm going to do the as follows. My algorithm will be kind of going through this tree, like in every node of this tree. And my goal is to compute the data structure, and the data structure at node D, A, B would contain all boxes except, so it would not gonna contain boxes from A to B. So this is what happened here, right? So we focus on the first block, and we build a data structure which contains everything but the first block. And then with the second block, we build a data structure that contains everything but the second block, and so on. And then for each such data structure that had one block empty, we filled it with elements one by one. Here, we're going to do it according to this tree. So, we start with an empty data structure here, and then we go to this guy, this V1 to 4. So we now want to have all boxes here except for boxes 1 to 4. So we have to add boxes from 5 to 8 on this edge. And we get a data structure like this. And then from here to here, we have to add boxes 3 and 4. And to get from here to here, we have to add just box 2. And here for here, we add box number 1, and so on. So, can you see how the algorithm is proceeding? Okay, so let us calculate how many add operations we have here. Well, maybe to calculate that, let's focus on some fixed box, like on box 3. When do we add box 3? So we have to add box 3 if we have the data structure which does not contain 3, and now we want to add it. So box 3 is here, or somewhere on the path. So we have to be okay, the data structures which do not contain 3 are the ones above it. And we add box 3 every time we're leaving this green path. So we're going here, and we're going here, and when we're going here. So this tree has log n levels. So then we conclude that for each box, there are log n add operations. So the total number of add operations is like n log n, which is much better than this one. And if you look at this number, what we'll get is n squared times log n times m, which is great, right? Because this algorithm here works with, this is like n times m. This is like n squared m. And what we get is O times n squared log n times m. So with the cost of a single logarithm, instead of computing the set of options for all boxes, we're able to compute it, the set of options for every n-1 element subset of the set of boxes. Now, what I would like to stress is that we assume really very little about what is happening here. So the same construction can be done for any data structure that just supports additions. We can perform construction like this only if we need to add boxes. This, of course, is just a concept of how this works. Normally, you want to implement it as a recursive algorithm that branches through and carries some data structures, but this is just a technical issue. This can all be implemented really easily, and using this technique, we get a very big speed up. Okay, maybe a few seconds to digest and ask some questions which you might have. Okay, so if you think that this is fast, I have a surprise for you. You can do even better. Yep.
Any operation
Costs, an operation costs n times n. Yep. N is n times m.
Yeah.
So
No, because all the n minus 1 you already have. You are adding one, just one. So the first four you don't have. Just the second.
What is the question about?
You are doing two loops.
Where? Here. No, here. Oh.
Yes.
So this is n, and this is m.
Yes. But when you add one more box, you don't have to do two loops again. Only one.
Yeah, but
the second.
I need to subtract, right? So I need to do, I can build it for all n boxes. And what I need to do then is, my goal here is to build a data structure for n minus 1 subsets. So I want to go box by box and say, okay, I have the data structure for all boxes, but I want to see what the data structure would be if I remove one specific box. So, you know, I have a data structure and with n boxes, and I want to get it from n minus 1 boxes. So it's not adding, so this would be removing, right? So it's the other way around. Yeah, so,
What
yes?
about the memory?
Memory. You mean with implementing this, right?
Yeah.
Well, okay, so what you might do here, so the good thing here is that the add operation takes as much time as the array size. So in principle, we can just create a new array, right? And not really matter. A simple solution would be to have one array for every level of recursion.
Isn't that too much?
Which might be a lot, but actually you can although add is not a reversible operation, if you're undoing the adds you did, you can do that. So okay, so add operation basically sets some ones here, right, in this array. So as you're going down an edge, you're setting ones. You can store those ones in a vector, and then you can undo this. And the total size of the vectors, of all vectors, because I'm only adding this one to a vector if some entry changes, right? So at every step, the total size of all these vectors would be like the size of the array. So you can really have like no overhead with the memory at all. Okay, right. Any more questions?
Cool.
Yes.
In the analysis of this first algorithm, you have n times n squared add operation, right?
I have this many operations, and this is the running.
Yes, add operations.
Yes.
And each add operation supposedly is n times n, right?
Yes, so it's, I multiply this one by n times n and I got this.
Yeah, but if you are adding only one box, right?
Yes, it's still n times m.
Adding one box is still n times n. Oh,
This is the operation of adding a single box.
it's not, alright.
Yeah, because you have to, I mean, array size has to be the number of boxes times the total size of one box, because it has to be able to hold up to, you know, it has to be able to hold the values of this size, right? That's why. Right, so this was first approach, and I already told you that this is not the fastest thing possible you can do. And again, we need to go back one step. So, as I mentioned before, we're doing this construction because our data structure only supports add operation. And if, in some magical way, we had also a remove operation, things would be much easier, right? We'll be able to we'll be able to, first build a data structure for all boxes, and then for every box, you can just remove this box, and we know the number of options, and then we remove the second box, and so on, and we'll know the number of options for all possible n-1 subsets of boxes. Okay, so remove operation. How to get it? Well, the real problem when we cannot do a remove operation is this thing, right? I mean, this thing might change this data structure or might not. Let's change the definition of the array. Before it was is I an option, and now I'd like to have it how many subsets of boxes have sum equal to I. So if this is 0, this means I is not an option. If this is more than 0, this would count the subset of boxes whose total size is equally I. So again, if this is 0, this is not an option. If this is greater than 0, then it is an option. And how to calculate that? Well, the change is slight. I just did it. So what happens now? I'm doing the very same dynamic programming, and I'm saying that, okay, initially 0, there is exactly one empty subset, which gives me option 0, and then I'm going to add boxes one by one. Here, I'm adding one box, and in order to add a box, well, to check options whose sum is j, I have my box of size ai, and if it is possible to get this total size of boxes, and we have that many combinations, then from each of those combinations, together with box of size ai, we get combinations of size j. So this number simply has to be added to this one in order to get what we need here. Now, this number might be a bit big, so let's calculate this modulo some prime number p. So this will have to be, okay, whatever. Let me write it symbolically. It's like modulo p. And this code does exactly what we want. It does calculate the number of ways in which we can obtain option of exactly I boxes. And the big advantage of this code is that now it is reversible. So if you look on this loop, like without even knowing what it does, we're going through some loop and doing some additions. What we're doing here, we can just do from back. I mean, maybe you don't even want to analyze what it's doing here, but this is like a mechanical operation without thinking what's happening here. So we're going to do the same loop backwards. So it starts with j equal to ai, and then j has to go all the way to 100 times 7,000, and j is increasing. And at every step, we're reversing what happened here. So dp of j, we want to decrease it by dp of j minus ai. And this all happens modulo p. Right? Normally you'll have to, here you'll have to say dp is equal to something plus p modulo p, and here you have to write this is equal to p, whatever, it's equal to the old value minus this value plus p modulo p, but I want to keep things short. So if you analyze it, this code basically undoes what the first one does. So in this way, we got an operation of removing a box, which also works in n times m time. So now our solution to the first stage of the problem is build a data structure containing all boxes in n squared times m, and then for every box perform a remove operation, remove this box, see what the number of option is, and then add this box again, and then go to the second box, and so on. And the total running time of it is n squared times m, which is actually really great because it's exactly the same running time as what we get for just computing the number of options for the initial set. So it's like as fast as the solution to the basic problem. Yes?
By adding the module P, those two are probability of failure.
Excuse me?
Probability of failure by adding the module. You can get like 0 with the something.
Yes, so obviously this is now a randomized solution. If we're very unlucky, then this thing, modulo P, is 0, although the number itself is not 0. If P is a random number, the chance of this happening is obviously very low. But also, we can fix it so that it wouldn't fail. I mean, this is kind of, I'll be cheating a bit, but you really can write a program which runs it this time, and I'm going to show it to you now. So let me ask you a question. What is the maximum possible value of dp of I if we don't take it modulo P? The upper bound. Yeah, it's 2 to the power of 100. There are that many subsets of boxes, right? So if dp of I is at most 2 to the power of 100, and we remember dp of I modulo prime number, which is, say, around 2 to 60. And we remember it also modulo some other prime number, which is around 2 to the 60th power, so like big primes that fit in long. And these numbers are distinct. Then, by, I think it's Chinese remainders theorem, if one of these, if this is a number that goes this big, and we remember it modulo two prime numbers, and this is not 0, then the remainder of one of those will not be 0. So it suffices to remember 2 long numbers to get like 100% probability that we're correct. As I said, it's kind of a cheating because this is well, I'm saying I have a constant number here, but it's like saying that long has a that this is, well, if long has a constant number of bits, then I'm treating this number as a constant in some sense. But so it's cheating a bit, but for this input data, you can implement it in exactly this time. Right, so that was stage 1, and we've seen 2 ways of doing stage 1 of the problem. So we're moving a box which decreases the number of options as little as possible. And now I think it's time for a break, and we'll meet in 10 minutes, so 11:15. And then I'll think what to do. We'll either do stage 2 or move to the second part of stage 2 will be an exercise for you. So yeah, see you in 10 minutes. Data structure which A does not contain A, B, I'm adding 3 to it. And the data structures which do not contain 3 by this condition are exactly those, right? And so I would actually like one of these data structures are going this way. I'm leaving the data here, going this way, right? You didn't have 3, but now you have 3. So there is like a really moment which I can read. So 3 is at all, it is only logarithms. Yes, so I have like a list which I did a budget position. This is exactly the reason why this is small, right? But I start my and I get most like 7,000 words. Since I don't number of chairs, okay, so it's like this one is this is head operation, right? This is M is the size of one box. So I want to be able to size 700,000. Be able to, because the biggest option I can have is the number of boxes times the size of one box. Yes, number of boxes, I think you have a number of boxes times the size of one box because the biggest Let's start the second part of the morning session. So I think we'll leave the second stage with an exercise. It's about totally different things. And I think the second stage alone is a very nice exercise about dynamic programming, and I think we should give it a try. We might not discuss it tomorrow, or alternatively, yeah, I think I know it. I'll link to a place where you can find the solution. So the second stage is let me remind you, it's about you're given a set of boxes and now you want to add the box of minimum total size such that the number of options doubles. That's what the second stage is about. And we know how to solve the first one. Once you get the second one, you'll get the task solved. Just maybe I should add that don't think that the Baltic Olympiad is all about tasks like that. This was actually way harder for an Olympiad. And no, even though you can find some good scores, it's not because people solved it, but it's more because tests were not as good as they should be. So yeah, it's from an Olympiad, but it definitely was way harder for them. Especially that it consists of 2 parts, and none of them is like very straightforward. Still think the second part is a nice exercise. Okay, so then, as I promised, in this part, I'd like to give you some tips on taking part in ACM contests. At first, like some very general tips for strategy and so on. And as a very last thing, I'll also like to give you some technical tips on writing, speeding up your code or increasing the space use. But let me start with a strategy. So if I think about giving advice for strategy, if there is like a single advice I could give to someone who is going to take part in an ACM contest, it would definitely be something like take it easy. This is what I hear when I'm talking to people who have competed. That it's very often the case that you finish the contest and you had like 2 solutions which you could not get accepted, or that you're very dissatisfied with the number of tasks that you solved. And surprisingly, it happens very often during contests, and it doesn't really happen during trainings, and well, I believe this is because people really tend to try way too hard during a contest, and while you should really try to relax. And the second problem during a contest is that you might face is that when you're doing not as good as you expected to do, and then it's really easy to get discouraged. I mean, you're looking at the ranking and you see that the top teams are way ahead of you, and I think it's extremely easy to lose your courage, but you totally shouldn't. I mean, I've seen contests in which the winners were like 3 tasks behind an hour before, and they still don't get there. And I've seen other contests in which people sold like 4 tasks in the last hour. So think of 4 tasks for the last hour. They're really the hard ones, and you really, if you really try, you can really do those. And I think it even happened once that there was a single guy in the team that just during the last hour by himself coded 4 solutions from scratch. So you can really do a lot with the last hour. You just have to keep working. But okay, so this is like a general advice, and now what to do during the contest. And this is some piece of advice that probably you might be partially familiar with, but I think it's very important to follow. Well, it's very important to do this consciously. So, okay, I'll give you some advice, and you can take it or not, and maybe I might be right or wrong at some point. But my main point is that you should have a plan. I mean, you should know what to do, and you should be prepared, and you should really know what to do in every minute of the contest. Don't just start taking part and without the planning and hoping that you'll decide and take some strategic decisions during the contest itself. What do I mean by that? So, well, what happens when the contest starts? When the contest starts, since because of the way the time is measured, the first minutes are very important time-wise. So in the first minutes, the time is much more important than in the next minute. Because if you lose 1 minute during the beginning of the contest and then you solve 10 tasks, this time gets multiplied by 10, right? Every single task will be solved later, and so every time you lost gets multiplied by a big number. So the usual strategy for the very beginning is that someone gets the tasks, opens the envelope or whatever, and has to distribute them. And of course, there are many ways for distributing tasks. One of them is random. One of them, which I like, is just look at the task like briefly for maybe 3 seconds, try to figure out what area it is about, and give it to the team member who is best at this particular area. At the same time, like the second the contest is started, someone sitting at a computer should start configuring the computer, writing some templates, and preparing the workstation for the others. It's, computer is a very precious resource, and you should really use it from the very first minute. So what usually happens is what usually we did is we just wrote some template for the CPP files. We wrote some make files so that you can just type make and compile a solution. We wrote a script that created a directory for a task, copied the template there, named it, for example, a.cpp, and also copied the make file there. And then, the next person that came can just type one command, and then the template was ready, the make file was ready, the directory was ready, and it took no time to start writing a new solution. What's often also done is that you have a semaphore, which is very helpful for coordinating what's happening. And a semaphore is like a piece of paper with a grid, like listing the tasks and your names here, like name 1, name 2, name 3. And what's happening is that in a cell, a person can write comments about a particular task. In particular, you can have the task assignment written here somewhere, and you write things like, don't even try implementing this, or I kind of know how to solve the first part, and if you ever want to start this, talk to me, and so on. And the goal for that is that, especially in the first minutes, you don't really want to talk too much probably. I mean, in the first minutes, you want to solve the easy tasks, and solving those that often does not require too much cooperation. So, apart from some short comments, I think in the very beginning, if you are a team, if you start competing as a team together for a long time, you should communicate with as few words as possible. So that's the beginning. And now let's move on to the workflow for solving a single task. And well, I think it goes as follows. The first step is read it. The second thing is think. And sometimes after these two steps, you know how to solve it. Sometimes you don't. If you don't, as I said before, you may try various things like try listing the techniques you know in your head, or well, ask yourself what is this is especially important for things like dynamic programming. So what is the minimum information that determines what the solution is? Try thinking in many ways. What is important is that if you're thinking and it's not working, then really what you should do is not try doing different things. Don't follow one path, but if you see it's not working, try a different one. It's if you keep doing the same thing, you should not expect to get a different outcome, even if you try many times. And also, one other thing I'd like to mention here is, I forgot about this. Whatever. Okay, so at some point, hopefully you'll get to the solution and you know what to do. And so you got the solution in your head, and then what do you do then? And well, you might think, okay, and then I go to the computer and I start coding it. And I think it's not a good idea at all. Seriously. Once you have a solution, before you start coding it, there is a part which is, I think, extremely important. Think about the solution, about the implementation. Think about data structures. Think about how you're going to implement it. Maybe is your first idea the best one for implementation? And it's often the case that I got this idea, I know how to solve it. You start solving it, and you don't even realize that what you're doing is like twice as complicated as what you could do if you spend a bit more time on thinking about implementation. This is a tip that was often repeated by my friend who was world champion ACM ICPC, and well, for me it helped a lot the moment I started using it, because you really can get your solution to be much easier if you spend some additional time. If you don't start coding it the very second you get the idea. Now, at some point you want to start writing the code, and then I think it's really important that what you write is a very clear and code and easy to understand. I think what actually happens with many people is that, well, if you're a beginner, you're trying to write some clear code because programming is new to you, so you really want to keep things clear. But then you're getting better, and you see, oh, I can do this faster. Oh, and I can use this trick. Oh, and I can save some lines here. Oh, and I need to save time, so let's maybe not use too many functions. Let's put everything together, and let's keep the variable names short. And what happens is that the code validation decreases. And then, for some reason, surprisingly, this is not what the champions do. I mean, I've seen the guys who win some very big contests, and what they do is a code of some great quality. So remember that, like, the sign of good programming skill is not that you can write everything extremely short, but that what you're writing is clear and easy to debug. After you're done with coding, it's time to submit. And it's a common strategy to submit a solution, and at the same time, before you even get the verdict, to print it, just to save a few seconds of time. grading may take a minute or two, and it can really save you a few minutes. When you submit, I think it also maybe it's not the best idea to tell all your team members, hey, I just submitted, because whatever they're doing, they'll keep watching what the submission result is, and you'll also take some time from them. So it's better not to let them know so that you don't distract them. And okay, after that, hopefully it works, but sometimes and then you're done. But sometimes it doesn't. So if it doesn't, you have to debug. You have the printout, hopefully, because you've sent it for printing. And you start reading the code, and then you find an error. The error is there because you got some bit verdict. And you get the error, and your first idea will be, okay, give me the computer, I have to correct this one. And I think this is a totally bad idea. This is, again, something I learned from my older friends. If you're reading a code and you find a bug, do not stop reading. Read the code to the very end. And it happened to me lots of times, then I found a second bug afterwards. And although it might be tempting to start to resubmit once you find the first problem, I suggest you really don't do that. Really read the code to the last line and try to find all problems, not just the problem. There really could be many. Right, so then you read the code, you've corrected the problems, you've submitted, and okay, it might work, then you're done. Or it may, well, also not work for some other reason. So then again, maybe you'd like to use the debugger for a few minutes. I don't think it makes sense to do it for more. And then again, keep reading the code again. And then one more time. And then if you still cannot figure out what's wrong, I think this is the time to ask a friend for help. And what we do usually in our teams in Warsaw is that you sit with a friend and you read the code to it, like explaining everything that is happening. And it's not really important that the friend understands what's going on. What is important is that you're explaining it with every detail and you're clarifying like every assumption that you have made. And because of that, what you're saying will be very detailed, and probably you'll find the problem yourself. And I know that this might sound strange. I mean, why would it be the friend who's not really listening? But maybe out of all advice that I'd like to give it to you, this has worked very unexpectedly to me, and it helped me a lot. And I think it also helped lots of my friends. Okay, so you read it to your friend. Sometimes you find a problem, but sometimes you don't. And then what do you do next? You don't find the problem. You still have another friend to help. And if you're really stuck and you have no idea what's going on, this is usually the time to give the task to the third person. And this is another important thing. If you do that, I don't think it's wise to say, hey, I have this task in which you have to do this, and this is my solution, but for some reason it does not work. This is a bad idea because if you have any false assumptions, or if you have misunderstood the task statement, or you have skipped some information from the task statement, you'll then give the same error to your friend. And this can be really serious. I mean, there is a team from Warsaw which was a world champion in 2007, I think. And the following year, they kept training, and they were like winning everything they could win, every training contest and lots of other contests. And then they went to world finals, and they were like, their chances of winning were great, and they made exactly this mistake. So someone had a false assumption, and he carried it over to his friends, and they got stuck with one task, and actually in the end did very badly. So it's really important to have one person who does not know anything about the task before getting it, so that you have a backup option, so that someone can solve the task independently. Of course, what I'm saying is, it's based on the strategy we usually have, that the tasks are more or less solved individually. There are also some other strategies, like we can do all the tasks together as a team, and I have no idea well, I'm not saying which one is better because I have no experience with the second one. But if your initial idea is okay, let's try to split work into individual team members, then it's really helpful to have a person who knows nothing about some tasks, just to have a backup. And then you ask your friend for help, and after all these steps, this is your last chance. But again, it's really amazing. It often helps to get the task accepted. So I think in my experience, after we followed all these steps, we eventually got every single task accepted. I mean, if we really follow this rule, so I think they are kind of useful. I mean, it's not that we always get every task accepted, but then in those cases we didn't really follow this. Right. So this is workflow with a single task, and now maybe some other advice is some general advice about what happens during the contest. Well, maybe one of the most important ones is be conscious about what is happening. So keep track of the time you have. Know how much time you have until the end, and try not to get emotional. Again, take it easy. So if you see that you're struggling with a task, and you really want to get the task accepted, don't just stay focused and forget about everything. Don't waste minutes with the computer trying to solve this one task. If at any point you'll notice, okay, I'm getting emotional, not thinking rationally about what is going on, just take a break, don't think for a few minutes, and just try to relax. Also, whatever is happening, it's a very good idea to take a break in the middle of a contest. Like after 2 or 3 hours, just leave everything what you're doing and have a 5 or 10 minute break. Don't think about the task. Get a snack and just relax. It really helps you, to regain your energy for the last part of the contest. What else? Well, try to fight for every minute. Really, try to optimize what you're doing. When you've submitted, like leave the chair as soon as possible and let your friend in. Don't waste time like looking on a screen and pressing F5. Whatever it is. You can let someone work, and then in a minute or two, check what the status is. And then make a plan. If it's like 1.5 hours to the end of the contest, you probably can see how many tasks do you need to solve to get to the place where you want to be. And then plan this work. Don't start doing too many tasks. It's often the case that there is an hour to the end. Someone is working on one task, another person is working on another task, and they're both big coding jobs. And then it's often not the best idea to start writing the third one, because you might block each other from the computer, and in the end you might not get a single one accepted. So try to be rational about how much you can get solved and solve those. At the same time, if you can see that you're not doing well, you have to be optimistic that you can do something, but don't be over optimistic that we can although this is like a huge coding job and there is lots of work to be done, don't try to start too much. But okay, so these were tips of many kinds. This was what to do at the very beginning, what to do at the task, what should be the attitude for the contest. But I really think that the most important one, and which I'd really like to stress, is remember to take it easy. So, right, this is what I'd like you to know about some of the strategies that we're using. And now I'd like to move to something very technical. In the last part, okay, let's start here. So for this, I'll need the whiteboard again. Yes.
How much time should we spend testing the program?
This really depends. So sometimes the policy is 0, and some teams really do that. Just debug.
I mean, before the first condition.
Oh, yeah, okay. So I don't know. I think people usually write 1 or 2 small tests. If you're worried that your solution might be too slow, you might want to generate a huge test and see how fast if it runs fast enough. But normally, I think you should see. Okay, first of all, whether the example is a serious test or is just some random numbers. If it's not, maybe try to write one or 2 tests that will test something. It really depends on the task, right? You have to have some intuition. Okay, this one requires lots of testing, and maybe in this one, like a single test is enough. So, but I think, like typically, 2 or 3 tests is what people do. And then the other moment when you spend more time on the computer is that if your program crashes on an example test, and then of course it may be actually easier not to read the code but to use some debugger, right? So if you compile your program with Word, if you compile your program with -G ACPC, and then you run it, and then it's crashed. So what you do then is you run GDB, and then it writes some stuff, and then you say GDB my program, and then you write R, which means run, taking input as input, and then it does something and it crashes, and then you write VT, and then it tells you exactly where it crashed. And this is very useful for debugging. I'm not sure you know it, but like if what you're doing fails on the example test case, this is very useful because it lets you find the precise spot or the precise line in which you had a problem, and then once you do that, you can also say something like print, like name of a variable, it will print you the name of this variable you had, so you can do something like print x, and this would output you the value of x. Maybe this wouldn't work with strings, but it will work for strings. Another thing you might do for debugging, this unfortunately is not available in all workstations, but it sometimes is. It's something that is called rend. And you run it like Belgrade, like program, giving the input, and it's doing a slightly different thing. It's just checking if your usage of memory is correct. So for example, it will tell you, it might take warnings like, okay, I'm running your program and I see that you're reading some memory which you have not initialized. So what you're getting is probably garbage. So it can detect these kinds of problems. So you might want to experiment with that and see what it says. Well, there are some problems with it. So if you compile your program with, I think, -static, I've seen Valgrind print some errors for programs which are correct. So if you're using that, maybe don't use static. And also, I mean, don't try using Valgrind for the first time in a contest, because what it's saying might be sometimes misleading, and you might think that it's a problem where there is not. So before using that, experiment on your computer. Okay, so that's for debugging. And now, if you want to read code, but the printout has not yet arrived. So as I said, don't waste this time. You can still read the code. So what you normally get in a contest, well, recently, this wasn't the case a few years ago, but now it's quite common to get a 16:9 widescreen. And if you're coding, you're probably using like that much coding. And this is not used. If you're using Linux, you can open some terminal here with your code. You can read your code here. Your friend can code here. And it's even possible to configure well, some machines are already configured like that. And at the same time, your friend can code here, and you can use the mouse wheel to scroll this one. So you can basically work together on one computer and read your code while your friend is working. This one was invented by my friend during a contest in which printing failed, so that's what we did. And it really worked very well. Right, and the next thing, let's move on now from some more practical stuff to hardcore programming. Speed optimizations. Okay, maybe this wouldn't be really new to you, but you might want to be interested in some of them. So, one of them is int times long is faster. It used to be. I mean, this list I prepared a few years ago when I was still competing. I hope the computers haven't changed too much since then. So multiplying integer by long is faster than multiplying long by long. So if this is what you really want to do, I mean, you want to multiply a big number by a small number. Don't cast both numbers to long. You can use this, and you'll get a considerable speed up. So of course you want to write it like x times y. The long should be first, so that the conversion is right. That's the first one. Second one, 2D matrices. What happens if you have a matrix like, let's say, 1024, maybe 2048 by 2048. You know this one?
Fits in the cache line.
Yeah. So if you have a matrix and its dimensions are, say, powers of 2, then for some reason things can get very slow. What happens here is that the computer and the processor is caching some parts of memory. So when you're using an array, it's loading some parts of memory into the cache, which is like a faster memory. And okay, I don't want to go into very deep details here, but what happens is that the location for a cell in the cache is often done by computing modulo some power of 2. So what happens here is that with an array of this size, for example, say all numbers in a column of the array have the same cell of cache assigned. Can you hear me? This is better. Yeah, I'm going to hold it like this. Okay. Doesn't help. The problem is here because the light is on. Okay, still works. Okay, let's leave it. I'll try to speak louder then. Right, so what happens here basically is that some cells of the array are loaded into cache, and then they can be accessed faster. But if it's a power of 2, then what happens is that this cell has the same location in the cache as this cell, and then as this cell, and so on. So the CPU is trying to speed things up, loads this cell in the cache, but then this cell has to be discarded because this one is loaded, and so on. And effectively, the cache does not help at all, because like every new cell replaces the previous one. And well, not going into details, sometimes if you write like +3 here, things can get much faster. So it's so the rule is don't make matrices whose size is the power of 2. It's safe usually to use some odd number there. This should work fine. And you can actually check that if you're manipulating size arrays by 1, sometimes it changes the writing time a bit. Not by much, but it can change a bit. Okay, number 3. This is a very specific one. This is for geometry. Rotations. Sometimes you have a geometry problem and you want to rotate some point by some angle. For that, you need to compute a sine of an angle and a cosine of an angle. So you have a function, compute a sine, and it gives you a sine. You have a function, compute a cosine, which gives you a cosine. But then, if you want to make this twice as fast, both these functions are slow, there is a function which computes both. So it has the argument and 2 pointers, and it gives the result. It has some return value, whatever. Okay, maybe I should have mentioned this in the very beginning. So all these tips, this is not like what you should do the moment you start coding a solution. And this is also not what you should do if you submit a solution and it gets time limit. This is something that you might try if you have submitted some solution and it gets time limit, and you have spent a good amount of time thinking, okay, can I make my algorithm faster by changing the algorithm? And is there probably a faster method to solve the task? And you really don't want to be doing that too early, because by changing the algorithm you can often easily speed the program by a factor of 20 or something. Those things might give you a speed up of, well, at most 2. So this is like, if everything else fails, try doing this, but don't try doing it too early. The next one, modulo is slow. This is a very slow operation, and don't do too much of modulo if you really don't have to. So for example, if you want to compute some value modulo p, and p is not too big, and for example you have some formula and you have a loop for something that x is increased by a, and then take it modulo p, then if a is not too big, if the a is, it's like a I. So we're adding some elements here, one by one. And if AI is not too big, it really speeds things a lot if you take this modulo every few iterations. Like you can do if I and 15 equals 0, it means something like basically every 16 iterations, make x modulo b. And this again gives a very big speed up, because this operation is very slow. It basically dominates. So this can give you a speed up of a factor of 4 or something. Yes? Excuse me?
Why not check if x is bigger than b?
Because this is not what you might want to do. Because if b is small, you might still be adding more without overflowing. You can even say more. Okay, but when you do that, be aware that you have to, you have to be sure that the final value as x is taken modulo. Like there is this extremely tricky case of type of tasks in which you have to output the value modulo p and p is equal to 1. And sometimes you do something like, okay, my result is 1 in the beginning. Say it's like combinatorics, whatever. So you're counting some object. You often start with 1 and then you multiply this by something. And then you do for some loops and there are some calculations with result. Take it modulo p. Everything seems fine. And then you print the result. Then it's wrong, because if n was small and you didn't get here, and you're printing the result, you're going to print 1. But if p is 1, then you should actually print 0. So if you have a task in which you need to get a result modulo p, always add modulo p printing, just to be super safe that you haven't forgotten about it. Okay, and the last one in this series is about the lists. Sometimes you want to have a list in your algorithm for many reasons, like you want to have a queue that has both ends. Sometimes you want to insert elements in the middle. But if you don't want to insert elements in the middle, you only want to have easy access to both ends, do not use list. There is something called deck, which is faster. And that's what I'm saying, it's considerably faster. As I said, it's not like it does, it provides the very same operations, but you can push a pod from the front or the back. It's also a container for a sequence, and it's considerably faster with a list. So what a deck is, conceptually, I think it's just a list, but every element is a vector. So there are some blocks, so your sequence is divided into blocks, and those blocks are arranged in the list. Okay, now that was for speed, and now let's consider space. So the first thing is, what eats a lot of memory? One is vectors. If you have a vector, assume that it eats like twice as much as it should for an array, because that's how it works. It allocates more than necessary, and it can eat up a lot of memory. So if you ever have a problem with space and you're using vectors, that's probably the best way to start. You can get the space usage down by a factor of 2 by removing vectors. Also, if you do something like dynamic allocation, let's make a string of 4 characters. How much space is it going to take? This one is going to take 16 bytes. Why so? It's just because if you're, okay, as I'm saying, I'm referring, this is, I think, implementation depends on the compiler version, library version, whatever. But at least some time ago, it was pretty common that when you did that, the minimum amount of space you could allocate was something like this. So if you allocated like 400, then it would be fine. You'll really use about 400 bytes if this was 400. But it's like maximum of what you have and something like 16. So bear in mind that this might eat a lot. And then in the remaining few minutes, how to optimize Structures. This is one I like. Here is this. So let's say we have a struct A, which has the following fields: character A, and then an integer B, and then a character C. How much space this is going to take?
12 bytes.
12 bytes. Why is that? This is because integer takes 4 bytes, character takes 1 byte, other character takes 1 byte, which gives 6, which makes no sense. So what happens here is that for some reasons which are not entirely clear to me, the compiler tries to align fields of a struct to 4 bytes. So here it's going to use 1 byte for the character, then waste 3 bytes so that the stuff is aligned up to 4 bytes. Then it's going to spend 4 bytes for the integer. Then it's going to spend another byte for character, and then another 3 bytes so that the thing is aligned. So this is 12 bytes. And from here, if you change it to characters A and C, and then integer B, then this one would take 8 bytes. Okay, how do we get it to 6 bytes? Well, okay, making it to 6 bytes is possible if the compiler you got is GCC. Say underscore underscore attribute double brace packed. Another 2 underscores here. 2 braces. Say packed. And then column. And then if you say this is like a magic instruction for the GCC compiler, then it's really going to use 6 bytes. And this might seem like a very technical trick, but actually it happened once that a team won a contest just because of adding this particular line. I mean, just decided on them getting a task accepted. Yep.
We can use in the first two, or you have asking?
I'm not sure. Okay. So probably you can.
But you're also making the access to those specific fields slower.
Yeah, okay, that's true, the access might be slower, but I'm talking about the case where the space is an issue. And the last one is, what if we need to have 2 variables, one which has numbers into few billions, another which is in order of a few 100,000. How to pack those? So in C++, you can do something like bit fields, which are variables of any size. You can write something like unsigned integer x, which is occupying only 20 bits. These are bits. And also, on top of that, you have unsigned long y, which is occupying 40 bits. So effectively, you can have 2 unsigned fields which occupy together 60 bits, so this will be 8 byte. And this is an unsigned number which can have values up to 20 minus 1. This is an unsigned number which can have values up to 240 of minus 1. and you can use them like just like ordinary integers. The only problem is that they should be unsigned, I think, because well, it's implementation defined. What happens if you say signed here? So implementation defined means you better not experiment with that because it might behave differently on different compilers and operating systems and so on. So this is helpful when you really want to pack lots of data into little space. Right, so that would be it for the tips for the contest. In the afternoon we meet at 1 p.m. and we have a team contest again. So see you at 1 p.m.
One more question. Oh, it's working now. A quick poll, because I was wondering about the topic for tomorrow lecture, and just a small survey. It's not going to decide about anything, but just something I'd like to know about. My question is, who of you knows the algorithm for range minimum queries with low entry processing and constant time answers? So it's about we're given an array of integers. We'd like to pre-process it in linear time so that we can answer a query like, what is the minimum in this interval? We want to do it in constant time. If you're not sure if you know it, you probably don't know it because it's like it's a few-stage algorithm. So my question is, does anyone of you hear about this one? Okay, one person did. 2, 3. Anyone else? Okay, we'll see that. Thanks.
Thank you.